Okay, so up to this point we've been dealing with just square roots and exponents that are integers. Now we're going to move into a little bit more complicated information, which is going to involve indexes which are greater than 2, and we're also going to be looking at exponents that are different than just being integers. So we're going to have fractional, or what we call rational exponents, to deal with. So let's take a look at this first problem here. We've got the cubed root of 125. So what this cube right here is telling us is that we need a number that when you multiply it times itself and then again by itself, you're going to end up with the number 125. So just to give you a look into the process that you're going to use, we could say 1 times 1 times 1 is equal to 1. We could say 2 times 2 times 2 is equal to 8. 3 times 3 times 3 is equal to 27. 4 times 4 times 4 is equal to 64. But then you get to 5, which is going to be 5 times 5 is 25, times another 5 is going to be 125. So the solution to this problem is going to be 5, because when you do 5 times 5 times 5, you get the radicand of 125. Now in problem 1b, we're looking to take it one step further. We need a number that when you multiply it times itself, times itself, times itself again, that gives you the radicand. So if we look at this, we do 1 times 1 times 1 times 1, we get 1. We do 2 times 2 times 2 times 2, and that's going to be 16, and that's what we're looking for here. So the solution to the fourth root of 16 is going to be 2. Now, you are going to want to memorize a lot of these, or at least up to a certain point, because there are going to be a lot that you see in the book or that you see on your assessments that are going to be repeated over and over and over again. So we'll take a look at what those are a little bit later on. In problem number 2a, what we want to do is we want to take this expression, 12a to the 2/3, and we want to turn this into a radical. So we're going to take a rational exponent and turn it into a radical. It's actually not all that difficult a process to do. Now remember that the exponent on this 12 is a 1. So we're going to treat these two differently. We're going to treat the constant differently from the variable. So I'm just going to pull the 12 over here, and that's just going to stay on its own, and then we'll come back to that at the very end. What I want to do with this a to the 2/3 here, the number that's in the denominator of the rational exponent, that's going to be your index to your radical. Then the numerator is just going to stay attached to whatever it is, whether it be a constant or a variable. It's going to stay attached to it as its exponent. So what we'll do is we'll take this 3 and we'll move it out in front, and again that becomes our index. So we get the cubed root. Anytime that you have a 3 in that denominator, it's indicating cubed root. Then the a stays underneath the radical, and we keep the numerator attached as the exponent. So your solution on this problem is 12 cubed root of a squared. You can see that 3 does not go into 2, so we cannot take any a's out from underneath this radical, so it's just going to stay underneath the radical as the radicand. In problem number 2b, we've got a slightly different look at the same type of problem. We've got 64a, but this time the 64a is within parentheses, and the exponent is on the outside of the parentheses, raising both things inside of it. So what we're going to do is we're going to follow the rules that we've already established. We know that this 64 is to the first power, this a is to the first power, and then we have it being raised to the 4/5. Now what I'm going to do is go ahead and distribute that 4/5 through to both of those numbers. And so what we're going to get now is 64 to the 4/5, and then a to the 4/5. So the next step in this process, we're going to look to see if we can take that 64 and break it down to a smaller base. And what we know is that 64 is the same thing as saying 2 to the 6th. And then that's going to be raised to the 4/5. And then you've got a to the 4/5 hanging out over here as well. Now, there is something else that I can do with this. Rather than breaking this down to 2 to the 6th to the 4/5, I could have broken it down to 2 to the 5th and 2 to the 1st. I'm not going to do that on this one though. You can check your book to see how that process goes. I'm just going to show you how to work it out from here. So what we would normally do is look to see if we can cross reduce, because remember that anytime that we raise an exponent by an exponent, we're going to be multiplying those exponents. There's no cross reduction that can be done here, so we're just going to end up with 2 to the 24 fifths a to the 4 fifths. Okay? And so what we'll do now is go ahead and take that and put that into a radical. And so what we end up with now is the 5th root of 2 to the 24th a to the 4th. Now the next question is how many of these 2's can we take out? Well, we know that 5 goes into 24 4 times with 4 left over. So we can pull 4 2's out of here. So we're going to go 2 to the 4th, 5th root of 2 to the 4th, a to the 4th. Now, when it gets to this point, your book actually takes that 2 to the 4th and that a to the 4th and just puts them into parentheses together and makes it 2a to the 4th. I'm going to go ahead and work this out because 2 to the 4th isn't too much for us to do. 2 to the 4th is 16, and so we get 16, 5th root of 16a to the 4th. Now, as I've mentioned with exponents and radicals, there's multiple ways of working these out. Again, the book answer goes a different route than the process that I took. There's probably 2, 3, 4, 5 other routes you could take to get to that final answer. It's just going to be determining which one are you most comfortable with and then using that. Okay, so in problems number 3a and 3b, we're actually going to go the opposite direction of what we just did in 2a and 2b. This time, we're going to go from a radical and we're going to turn it into a rational exponent. So all we do in order to be able to do that is take our index and put it up underneath the exponent that is attached to the radicand. And that is just going to give us the fraction we need, which is going to be 3 fifths. So the solution to this is b to the 3 fifths. It's as simple as doing that. What this is going to allow us to do is to take radicals with different indices and perform operations on them. So addition, subtraction, multiplication, or division. Over here on problem number 3b, it's the same, we're going to do the exact same thing. I'm going to show you the longer way of doing this, just to show you what all the thought processes are behind how we do this. You could just look at this cubed root of 27 and say 3 and be done with it, and then move on to the d to the 5th. But you're going to be doing some other work later on that's going to require you to be able to break down your bases to even smaller bases like we did in the last problem. So what I'm going to do with this is I'm going to take that 27 and I'm going to break that down as much as I can. 27, the smallest base you can get with 27 is 3. And when you take it down to a 3, it's 3 to the 3rd. So 3 to the 3rd is equal to 27. Then you have d to the 5th. So now what you're going to do is you're going to take that index and put it up underneath both of those numbers, or both up underneath both of those exponents. And so now you're left with 3 to the 3 over 3 and d to the 5 over 3. Okay? And so what this becomes now, 3 over 3 is 1, so this is just 3 d to the 5 thirds. And that's how we take it from the radical down to the exponential form. All right, so in problem number 4, we're going to take all that we've learned and we're going to apply it to a word problem. So we've got Cleaver's law, which is the relationship between the metabolic rate and the mass of the human or the animal or whatever it is you're trying to measure. So we're looking at, if we have a dog that is 18 kilograms, then what we'll do is we'll put 18 in for the mass and we'll work this out. So we're going to go 73.3 fourth root of 18 cubed. So just to show you what this would look like in terms of rational exponents, we would take this to 73.3, and then that 4 is going to go up underneath there, and it's going to become times 18 to the 3/4. So what we could do is we could put this, either of these, into the calculator, and we're going to get approximately 640.6 would be the number of calories burned based on the mass of the animal. All right, so here in problems 4, 5, and 6, all we're looking to do is simplify some problems that have rational exponents. So we start with 81 to the 1/4. Now, there's a couple of different ways you could do this. You could look at this as the 4th root of 81, or what you can do is you can take that 81 and you can break it down as far as it can go. So doing that's actually the preferred method because we're going to need to do that a lot in the future. If we go with 81, we can change this into 3 to the 4th. And then we've still got that 1/4 exponent hanging out on the outside. So now what we do is we say, okay, if we're raising an exponent by an exponent, then that means that we're going to multiply them. But since we've got 4 over 1 and 1 over 4, those 4's are going to cancel, and we're just going to be left with 3, which is the same answer as what you get over here. The 4th root of 81 is 3. So we're going to use this method on this problem here, 64 to the 3/2. If we take 64 and we break that down as far as we can, that's going to give us 2 to the 6th. So we're going to go 2 to the 6th and then raised to the 3/2. So the 6 and the 2, this is going to become a 3, this is going to become a 1, and so now we've got 3 times 3, which gives us 9. So we get 2 to the 9th, which is going to be 518, 524, 512. So we're going to get 512 here. Now, you could go back and you could do it this method as well. If we were to do it with this method, we're going to get the square root of 64 cubed. But that really doesn't help us a whole lot. So what we've got to do is we've got to break that 64 down anyways, and we've got to say this 64 breaks down to 2 to the 6th, and then again raised to the 3rd. So then we get the square root of 2 to the 18th, which would then give us 2 to the 9th, which would again give us 512. So again, you can use either method that you want, but you're going to be using this method probably more often in the future, so you want to get comfortable in doing that. This is an example. Here we've got 2a to the 2/3 times 3b to the 1/4 times a to the 1/3 times 5b to the 1/2. So again, my first suggestion to you is to go ahead and just, anything that looks alike, put it next to each other. So we're going to take any constants that we've got first, and we're going to go 2 times 3 times 5. And then I'm going to go in alphabetical order, a to the 2/3 times a to the 1/3 times b to the 1/4 times b to the 1/2. Now, if you need to, go ahead and cross everything out as you write it down here. That way you know that you've actually taken care of every single thing that's in the problem. So we look at this, 2 times 3 is 6, times 5 is 30. Then here we get a to the 2/3 times a to the 1/3. So we're multiplying bases. Remember that whenever we multiply bases, we're going to add the exponents. So we get 2/3 plus 1/3, which just gives us a to the 1st, or a. Then over here we've got b to the 1/4 times b to the 1/2. Again, we're multiplying a base times another base, so that means we're going to add the exponents. So 1/4 plus 1/2, this is the same thing as saying 2/4. So 1/4 and 2/4 is 3/4. So your solution is going to be 30ab to the 3/4.